Good morning, everyone. Can you please confirm if you can hear me? Let me ask a quick poll question. Can you hear me? Yes.
Yeah, Enoch, it's audible.
Awesome.
So you might want to give the giveaway first for
All
the
right.
people who have participated in the quiz. And by then, the people are going to join and we will take it further.
All right. So let me quickly share my screen. And we have about, let me check. We have about 282 people that have participated in the quiz that we have posted both on Facebook and LinkedIn. And now we are going to randomly pick one person and then we are going to give them a gift. So let me do a quick, just to be fair to everyone, we are going to randomly pick the person. So let me find the random number generator and serial number 1 till serial number 282. So I'm going to put 1, I'm going to put 282, and the moment I click on the generate button, whatever the number that comes up on the left, that person is the winner of today's lucky draw. So without any further delay, let's do this. 3, 2, 1, and go. So the winner is the person with the number 22, serial number 22. So let's go find number 22. And it's Anuradha. So Anuradha, congratulations. And we will get in touch with you. We have your details. We will get in touch with you and we'll give you the gift card. Thank you so much. And today, watch out for our WhatsApp groups. We will be posting the links to the quiz after the session. And
Yep.
over to you,
Congratulations, Anuradha. And I really appreciate everyone who is participating and then contributing. And then, yep, that's an amazing thing. So, Enoch, would you mind posting even the WhatsApp link here?
Uh, I'll do that. So let me do this. Whoever is not yet part of any of our WhatsApp groups, just put up your message and I'll private message you the WhatsApp joining link. So the moment someone types in that they do not have WhatsApp, they are not part of any WhatsApp group, we are going to privately message you the joining link. Yeah. Over to you, Buddy.
Wonderful. Yeah. So please post the YouTube link. Sorry. Yeah. People who haven't watched, I request you all to watch this. So we are going to post this on the sticky note also. Enoch would do that. So let me share my screen and let me show you this. No, there won't be any assignments for this. Yeah. Assignments is part of our a different program, which is a full length. Here, assignments do not make sense because um, assignments won't be straightforward and then it's just going to cause a lot of confusion. So here we have all these videos, 9 videos. The ninth one is live now. So you have roughly 8 videos which are available. I request you all to watch these videos. Each video will be for 3.5 hours long. Okay. And watch it and try to make best use of that. And please do not forget to subscribe so that you're notified whenever there are newer questions which are posted. Okay, having said this, there are 4,447 people who are viewing these videos. That's amazing count. There are 9 videos, 8 of them are there, and the ninth is today. We'll continue in this way, and whatever we can complete in 20 days, we will do that. So today is the ninth day. All right, welcome once again, everyone, to this session. As usual, we will do a quick recap even before we proceed further. Our mind map has been updated for AI and deep learning. Here is a mind map link because this mind map also has the other details, such as you can access data science, cloud computing. We will have in comprehensive cloud computing AWS, Azure, Microsoft Azure, Google Cloud Platform, and IBM Watson. All these would be available. And if someone wants to go with AWS Cloud Solution Architect, that is also available. If someone wants to get themselves accustomed to only machine learning using Python and R, they can do that. If they want to proceed further with data science, that is also available. Big data, Hadoop and Spark, we have that. So all these mind maps are not something which is static. We dynamically keep updating these mind maps once in every week, once in every 2 to 3 days, something on those lines. So each time you view that, you will see a new list of entries. So I click on this. So here are the new things on the mind map. We believe this mind map should serve as a one-stop solution for everyone. We believe it will serve that purpose. So if you look at project management methodology, we started off by discussing about crisp DM, wherein we have this understanding the business problem, then you collect the data, then you cleanse the data, and then you proceed further with supervised learning or predictive modeling. In this, you have a lot of black box techniques, wherein we have neural networks. Okay, and these are the various networks which exist, in which we have already discussed about perceptron algorithm, and we discussed about multi-layered perceptron algorithm, and we will also discuss about CNN, RNN. But CNN has a very strong correlation with computer vision. And that is the reason we are now discussing computer vision and image processing stuff, in which we discussed about the various challenges that we have. What are the various image transformation techniques? We have point operation, local operation, and then global operation. Then we have discussed about noise reduction techniques such as moving average, 2D moving average. What do we mean by a filter, kernel, mask? We discussed about these. Then we discussed about how to handle boundary effect by doing padding, zero padding, wrapping, clamping, mirroring. And then we have also looked at template matching. Until here, we were able to understand. Now we need to take this discussion further and discuss about a few more things. And alongside, we have been using OpenCV, which is a de facto library which is used to handle computer vision applications, to handle computer vision and image processing kind of applications. Okay, so there we go. So OpenCV is something that we installed and we have done a lot of operations. And I need to quickly, sorry, need to check here on until where we have, you know, discussed in terms of programming. Is this a last one or okay? Yep. We discussed until how to split the various color channels, right? That's, I think until there we discussed. And we split the color channels into red, green, and blue. Okay, and the code is very, very clearly visible. The data sets are uploaded on your learning management system. I mean, the image that I use, I'm going to upload. And you will have to actually ensure that you look at this code and type it on your computer. That is exactly what we are interested in. All right. So I'll have this open so that towards the end I again post that. So now I think it is time that we get started with computer vision. And we will get started from where we have left. Edge detection. So if at all an image is provided to you, we know for a fact that image can be split into multiple rows and columns. In some sense, these are called as pixel intensity values. Each of the pixel value ranges from 0 to 255. 0 means black, 255 means white. So you have black and you have white. And you take each of these pixel values and you load them into your data set. So you can move this and make your data look structured. Whenever you have limited data at your disposal, when you have less number of images, etc., then what people usually do is they manually extract the features. You manually extract the features and like pixel intensity values. Pixel number 1, pixel 2, pixel 3, pixel 4, 5, in that way. You take all the pixel values and all these pixel intensity values will start behaving like your inputs. And output could be, is this a cat or is this a dog? Those kind of things. The good part is, if you can convert your images, which is unstructured in nature, Okay, and if you can convert this to a structured format, then you can use this structured data. Okay, and then you can actually uh, apply your traditional shallow machine learning algorithms. Like you can apply logistic regression or support vector machine or KNN or naive Bayes or any of those. Okay, just a moment. I think there is some noise which is disturbing me. Okay, sorry about that. Someone's vehicle. Okay, so this is the beauty, right? And another good part here is if you manually extract the features, another good thing is you will retain the interpretation part. You exactly know what is being extracted. You know that these values inputs are pixel intensity values. At least you know that these are the inputs. However, on the contrary, if you use these images and supply these images to your deep learning algorithms, and nowadays deep learning means neural networks, okay, different neural network algorithms. Okay, when you give it to your deep learning algorithm, features are automatically extracted. Automatically features are extracted. When features are automatically extracted without your effort, this is certainly a good thing, right? Because you're not doing any manual extraction, so you're saving a lot of time. While this is a good thing, the bad part is there is no interpretation. The new features that are extracted, like these new inputs, you don't know what those are. Okay, no interpretation exists. There is also another thing, wherein if you all are aware of regression techniques, when you write the regression model like this, okay, then you can easily interpret these values. What do I mean by that? Say you want to predict on what will be the weight gain of a person. That's the output, assume. So weight gain is equal to maybe 12.9 plus 1.6 into calories consumed, okay, plus 1.2 into age. In that way, you will get these numbers. And then you can use these numbers, calories consumed and age. You can substitute in this equation, and then you get the weight gain in typical regression techniques. Okay. And this 1.6 means that for every 1 unit increase in the calories that you consume, that means calories are measured in kilocalories, right? Usually. So if the calories consumed increases by 1 unit, the weight gain increases by 1.6, all else being constant. Okay, if you increase the calories consumed by 1 unit, I mean 1 kilocalorie, then weight gain or the weight will increase by 1.6. Yeah, weight if it is in grams by 1.6 grams in that way. But then when it comes to your neural network, you'll have an equation like this: B plus W1x1 plus W2x2. You'll get some numbers like the numbers that you have here. But those numbers will have no such interpretation. So one is the parameters that your model learns, the weights that your model learns have no interpretation. Another thing is the features or the inputs which are automatically extracted would also have no interpretation. But if you're working in, say, life sciences, healthcare kind of scenarios, okay, and in life sciences, healthcare kind of scenarios, when you build a, say, cancer prediction model, without interpretation, Medical Council of India or any of the governing bodies will not approve your model for usage, right? For usage in hospitals, etc. They will not allow. They will say, hey, there is no interpretation which exists. Why do I need to even rely on the model that you have built? Okay, so to counter that, people use these kind of shallow machine learning algorithms for which you have to manually extract the features. The first raw feature that is extracted is your um pixel intensity value, and the next raw feature which is usually extracted is edges, and that is where we are. This is called as snakes and saccats image that you're seeing here, and you get an illusion. When you look at this, you get an illusion that these snakes are rotating, right? But in reality, none of your images here are rotating. You get an illusion, right, that these images are rotating. You get such an illusion because of the edges in the image, right? Because of the edges that you have, you feel as if it's rotating, but actually it is not rotating. Okay, this is called as snakes and saccats. Okay, all right. And a few years back, if you remember, people have posted this image, and this image became extremely famous. Do you know what this image is? This image is an image taken by Mars rover. The robot which is used to explore planet Mars is called as rover, Mars rover. Okay, and Mars rover keeps taking the videos and images of planet Mars, and it explores planet Mars. And this image, people thought this is a woman, okay, and she has just fetched, they thought that this is water, and she is standing there fetching water from the pot, okay, and then yeah, that's what people thought. But ideally, when NASA has actually figured out further on, is it really a woman? Do you think life exists on planet Mars? Because Mars supposedly is very close to Earth, okay, in terms of various things. And that is the reason why they thought it's a woman. But then later on, they figured out that this illusion that is created is because of images, shadows. Okay, that's a slight motivation for you all to understand about edges. Now here, if you look at an image, as I've told you, image contains pixels, which is the most raw feature which can be extracted. When you feel that you can analyze the pixel values and use it for your further analysis, then the disadvantage here is that you need to use all the values, all the values, all the pixel values, and place it. Your data set might become extremely large. If your data set is extremely large, it takes a lot of time to do the processing. Hence, what people thought is, can we not extract only the edges? And if you look at only to figure out on what is there in this image, do you need all the pixels? Do you need pixel 1, pixel 2, 3, 4? Do we need all these pixels? Absolutely no. You just need the edge pixels, maybe. And that too, you need not have the entire edge. Just a few edges are good enough for you to say that this is a human in the image, this is a horse in the image, and this is an airplane in the image. You can make out just by looking at the edges. That too, you need not look at all the edges. You can look at only a few of the edge pixels, and you can make out on what that image is. Okay, then it is much more compact than all the pixels put together. It will be very, very fast in terms of processing. Hence, it is very important for us to understand about edges, which are also a few features. Like you have pixel intensities, we also have edges, which are also features, which can be extracted and used for your predictive modeling. Okay, and then edges are caused by a variety of factors. For example, whenever there is depth discontinuity, you'll have an edge. For example, depth means how far or how close objects are to you. If you look at this building, this is close to you in comparison to the sky that you're seeing here. You have sky and you have building. Building is much closer to you than sky. So there is that depth discontinuity. Hence, you'll have an edge over there. Okay, you'll have an edge here. And in comparison to this building wall, this railing is much closer. So there is again depth discontinuity. This is far, this is closer. So there'll be an edge here. Whenever there is illumination discontinuity, meaning here it is bright, here it is dark, bright and dark. So you have an edge over there. Surface color or surface appearance discontinuity. Here also you have an edge. So for example, this is of a different color and this is of a different color. So you'll have an edge over there. Then you have surface normal discontinuity, meaning if you go around this, there is an edge over there. Okay, and also look at this edge. Where do you find edge in order to understand that? This is the intensity representation of your image. You have an image, you're representing that image using intensity values, and here you have a function of x comma y, which is nothing but intensity values, and then you have your x-axis here and you have your y-axis here. You have your x and you have your y and you have your intensity values. Here you'll have 0 and here you'll have 255. 255 means white, 0 means black, right? And if you observe it carefully, if you take this portion, it's all white, 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 white color, white, 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 white. Then it is light gray, and then it's black. So if you look at this portion exactly, there is a sudden change in the intensity values. There is a sudden change. Here it is white and here it is black. So I mean suddenly from around 250 or whatever be the values which are closer to 250, your pixel values are switching to black. Hence there will be an edge. Here also it's the same case. You'll have an edge. So you'll have an edge like this wherever you have a sudden change in the pixel intensity values. Wherever you find a sudden change in the pixel intensity values, there will be an edge. Same is the case with this also. Suddenly there'll be an edge. Again, suddenly there'll be an edge here, here, and then here. Okay, so change in intensity values is determined using rate of change. The rate at which the pixel intensity values are changing from here to here is called as rate of change. Okay, rate of change is sudden change in the pixel intensity values. Rate of change is also called as slope, which is also called as derivative, which is also called as gradient. Hope you are aware of these things from our mathematical foundation session, which was covered earlier. Okay, so rate of change is also called as slope or derivative or gradient. So let's look at this derivative. All mean the same. Each of these mean the same. That means if you find the derivative of the function, derivative of this function, you remember images can be represented as functions. So if you find the derivative of the function, wherever the rate of change is the maximum, that is where you'll have an edge. So say this is a function. Edge means wherever you have a sharp variation, maximum change in pixel intensity values. So what do? You just take the first derivative. And when you find the first derivative, look at that, what's happening. It's all same here. So it'll be the same here. It's changing. So it will start changing. At some point, the rate of change is becoming stable and then it's getting stabilized here. So it's coming down and here it will actually get stabilized once again. So here you have maximum rate of change and then that is where you'll have an edge. To explain this better, let us take this another image. Okay, so this is an image that we are going to discuss about, but then do not mistake this red line to red color. No, this line is only there to represent that we are going to take only this row chosen for analysis. Okay, this is the row which has been selected for our analysis. Okay, hence it is just differentiated by using a red color. That is by no means a red color, just that's a row from this image. Now, if you take only this row, what's happening here is it's all white, 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 white color throughout. And there's a small transition from white color to gray color to black. So white means 255 and black means 0, right? So it's all same until there. And then there is a slight transition from white to black. So you have a slight bend. And then you have to come to black because suddenly it is black. So you come to black. And then it's all black, black, black throughout here. Throughout it is black here. And then there is a slight transition once again from black to white. It goes to slightly changes and then it becomes gray and then it again ventures into white color. If you have such a representation, okay, and if you find the first derivative of that, what happens? Yeah, it's something that we need to look at. So you find the derivative basically. This is, you're taking the image, you're representing that as a function of intensity values. Okay, so you're just taking one single row and representing that as a function. Once you represent an image as a function, you can find the derivatives. You find the derivative of that. And you find the first derivative. So what you do is it's all same, constant 255, nothing is changing. And then slowly it is changing. Okay, and then again it gets to the 0 part. So again you go back. This is 0. Okay, this is 0. Okay, so again it stabilizes to at 0. There is no rate of change here. Rate of change, wherever the rate of change is constant, derivative values or rate of change will be 0 because there is nothing which is changing here. Here also there is nothing which is changing. So the derivative will be obviously 0. And here also nothing is changing. So the derivative would be 0 in this portion. Okay. Then what's happening? There is a slight transition again. It's going upwards. So the rate is changing, rate is changing, rate is changing. And then the rate is getting stabilized. It's coming down and then it's becoming 255 there. So if you find the first derivative of this particular function, it appears like this. And here you have two extrema. One is this extrema is the minima and this extrema is maxima. And you'll have edge over there, you'll have edge over here. Look at that. You'll have an edge here and then you'll have an edge here. That is exactly what is being represented in this way. So it is that simple. Finding out edge in an image is this simple. You need not worry too much in terms of identifying the edges. Okay. So just to tell you here, you can also look at a function in this way. Okay. So what's going to happen is if this is your image will have x-axis and y-axis. It's a 2D. Image is a 2D representation. And you have x and y. All right. And say you have a pixel value here, which is x comma y. Some number, some x comma y. At this point, you will have some intensity values at this point. Okay. And then when I say x plus 1 and y, on y-axis it will be the same. This is x. So x plus 1 means you move by 1 pixel towards the right. And you'll get a pixel here. So you have pixel here. You're moving by 1 pixel. Since you're moving by 1 pixel here, you'll get function of x plus 1 comma y. So you take the pixel intensity value here and subtract it from the previous pixel intensity value. You're dividing it by 1 because you're moving only by 1 pixel here. So the change in x is 1. And that will give you the rate of change from this pixel to this. From one pixel to another, the rate of change can be captured. But this rate of change you're trying to find only along the x-axis. This is partial derivative of your function with respect to x. Now understand how important the optimization module that we have done is from mathematical foundations. Yep. Another thing here is if you have a value here, pixel value, okay, x and y. Now instead of x plus 1 comma y, if you were to do this, x comma y plus 1, then what's going to happen here on x-axis? It will be the same. Y, you're changing from y to y plus 1. So you're increasing y by 1 pixel. And you want to find the difference between the intensity values here to here. That's this. For that, you have to find out derivative of the function with respect to y-axis, with respect to y. Earlier it was with respect to x. And it will be approximately equivalent to f of x comma y plus 1 comma f of x comma y. This is f of x comma y. This is x comma y plus 1. And you are moving 1 pixel along the y-axis, so it's 1. The rate, the change along y-axis is just 1 pixel, so it's divided by 1. And then you solve it, you get to know what is the intensity, pixel intensity values which are changing along y-axis. Here we go. If you take this image, tigers. By the way, I think India entered into a world record in terms of the increase in the population of tigers. Right? We went on a mission to save the tigers, and the end result is too many tigers are out there. Yeah, that's a good thing for us. They didn't go extinct. Okay, so if you find the pixel intensity values, and if you find the derivative with respect to x, meaning along x direction, so you move from left to right, and wherever there are pixel intensity changes, you record that. Simple. So for example, say you're moving from this direction to this direction, you keep moving in that way, keep moving. Okay, you keep moving, and here at this point of time there is a sudden change. You're moving from this black color to white, so there'll be a sudden change in the intensity values. Then again, if you move forward from it, it's going to change from white to black, and hence there is another edge there. Again it's changing, so again there is an edge. So wherever you find such changes, okay, in the pixel intensity values, even at this nose, right, for instance, if you, yeah, if you move in that direction, there'll be edges. Wherever there is sudden change, there'll be edges. Very simple. Okay, so if you're moving along x-axis, what edges are found? This kind of edges like this, edges like this. These are called as vertical edges. So if you move along x-axis, the direction in which you move, in that not in that direction, but in the opposite direction, you'll find the edges, because you're moving along this direction, right? You're moving like this. So wherever there's a rate of change, you'll have an edge like that. Okay, so you'll get vertical edge if you move along x-axis. And if you move along y-axis, if you want to find the rate of change along y-axis here, along this, then let us see what happens. So if you're moving from in this direction, in this way, wherever there's a change, if you're moving along in this direction, so observe here there is prominent change to black color, so there is that edge. Then after the black is done, white starts, so there is an edge. Again, after the white stops, black starts, there is an edge in that way. So you have y-axis. If you move along y-axis, you'll have rate of change, and this rate of change that you're seeing here would have horizontal, would help you identify what edges along this direction, like this. Okay, edges like this. So these are horizontal edges. Okay, so you can identify vertical edges or horizontal edges based on whether you're finding the derivation of that function with respect to x-axis or with respect to y-axis. If you find the derivative with respect to x-axis, there will be vertical edges. If you find the derivative with respect to y, you'll have horizontal edges. Next, there is also one famous edge detection filter, which is called as Sobel filter. We will do all of these things practically, okay? Using OpenCV, we are going to do all of these things. Remember simple one thing, that if you have zeros here in this way, it will find vertical edges. Okay, for example, if you're moving, why vertical edges? Because if you see, you're looking at the change from 1 to -1, 2 to -2, 1 to -1. These values, a guy by name Sobel has experimented a lot and figured out that these values, if we put in a filter, it is going to help detect the edges. So that's why we are directly using that. How did those numbers come in? There is a mathematical derivation once again. Let's not get into that. Usually if it's our, there is another advanced training of this. In that we explain about the mathematical derivations also. But here I think it's not needed because you all are getting introduced to this for the first time, right? That's the reason. Okay. So if you move from left to right, you have zeros. If the zeros are along vertical edges will be identified. Let's see. So if you move from this direction to this direction in that way, yeah, here there is a sudden change. So there will be an edge. Then after the white is done, there is an edge here. Then here there is an edge. Then if you move in this way, there is an edge. Then it's the same thing. Okay, so you find the vertical edges. Then you can also find horizontal edges. The direction in which the zeros appear, in that direction edges are formed. So what happens here? Vertical, horizontal edge means you move in a vertical direction. You move in this way. In this way. If you move in this way, from here to here, there is that change, sudden change. So there'll be an edge. And then from this to this, there is again a sudden change. You'll have another line like that. And you proceed further. Okay, so horizontal edges are identified here. And then there are a lot of other edges, edge detection filters, such as Previtt, Sobel. This identifies edge along which direction. Let me ask this question to you guys. Okay, this one which I've highlighted identifies edge along which direction? Let us see. I'm going to ask a question here. A quick poll question. Along which direction are edges identified? Vertical or horizontal? Yep. Can you answer, please? Can you answer the one which I've highlighted? Along which direction do you think it is going to identify the edges? Sorry. Vertical. Absolutely. Absolutely. Whichever direction you have your zeros. Wonderful. And here it will help you identify edges along horizontal direction. In Sobel, along vertical, along horizontal. And then you also have Roberts. In Roberts, you find the edge along the diagonal like that. Diagonal. Edges are found along diagonal direction. So let us understand this quickly. This is called as grad. Grad means rate of change, gradient. The symbol is grad of function. So you find the derivative along x and also you find the derivative along y. Okay. If I say derivative along y is equal to 0, then you find the derivative of the function only along x-axis. If you find the derivative, if this part is 0, then that means you find the derivative only along the y-axis. And then you have something called as theta. When you find the derivative along both x and y, then you will have that angle theta. Theta is equal to tan inverse of derivative along y divided by derivative along x. That's tan inverse. So you have tan inverse of derivative along y divided by derivative along x. Okay. Now let me take a noisy image. When I say noisy image, there'll be a lot of noise. If you observe this image carefully, this is not completely black. This portion is not completely black. You also have certain dots, right? It's not pitch black. I mean, you have to get very close and observe. It's not completely zero. A few of them are 0, 10, 15, right? You know that 0 means black and 255 means white. But then if you, even if you have a value such as, you know, 10, 20, 30, they are still close to black. They're not pitch black, completely black, but they're close to being called as black. And also when it comes to white, this portion is not completely white. Okay, you'll have certain gray spots like 240, 250. They are not completely white, but then they are very close to be called as white. Okay, they are very close to be called as white. So here, when you take this and plot it as a function, okay, the values here are varying like this. They're varying. They're not exactly, it's not a straight line like that because all these values are not exactly zero. They could be 10, 12, 13, whatever be it. And then here also you have the same thing. Those changes are there. And when you have such a noisy image and when you're dealing with such noisy images, what do you think will happen? When you find the derivative of this function, because you know what? You want to identify edge. And if you want to find the edge here, you need to find the derivative. If you want to find the derivative, okay, then what should you do? You have to find the rate of change, which is differentiation, derivative. When you find the derivative here, what do you think will happen? Whenever there is a rate of change like this, the derivative will be high because you're finding the derivative this with respect to that, this with respect to that, this with respect to that. So there'll be huge fluctuation in your derivative also when you find the derivative of this function. This is what you get. Here you're kind of confused. Your model will be kind of confused on where is an edge because it's fluctuating by so much. Since it's fluctuating by so much, how do you identify on where is the edge? Okay, so you take a function. In order to solve this, okay, I'm now explaining you on how to address this issue because you cannot identify an edge if there is noise in your data. And if you have noise in your data, you need to address that. How do you address this? So what we do is you take a function and you take a Gaussian filter. Remember we discussed about Gaussian filter, box filter, etc. Once again, I repeat, guys, please watch these videos. They are not here for fun. Okay. So I request you all to watch these over the weekend because when you watch this once again, your understanding will become very clear. At least watch the previous day recorded video before you come to the next day. Okay. And trust me, if you keep doing in that way, your understanding will be super clear. At least I would say 60% of your artificial intelligence and deep learning part would be clear. Another 40% you can explore or you can enroll for the advanced program, etc. Right? But your understanding will be clear if you watch the videos. Okay, now back to this. So this is Gaussian filter. You take your Gaussian filter and then convolve it on this image. Convolve means it's like, as I've told you, addition, subtraction, multiplication, division. In that way, you have something called as convolution, right? So you take this filter, convolve on this image. The moment you apply a Gaussian filter on this, your image, resultant image, will become smoother. Look at this, the difference from this to this. It is a lot more smoother. Okay, and hence this Gaussian filter is also called as smoothing filter. Okay, it's called as smoothing filter. And then on this image, so what you have done is, as part of these steps, you have removed the noise, okay, from your image. The moment you remove the noise from your image or from your audio signal, whatever be it, audio signals are, audio or speech is one dimensional, images are two-dimensional signals. That's it. You need to understand this. Now, when you remove the noise from this, and when you get this image, which is a denoised image, which doesn't have any noise, now you find the derivative of this, and wherever you have a peak, that is where you'll have edge. Okay, look at that sudden changes here. So this is where you need to have edge. That is where you'll have an edge. Maximum change in the intensity values. Then there is another shortcut. Okay, here, what are we doing? We are first taking the Gaussian function. You're convolving this on this. After that, you get this result. On that, you're taking a derivative. But the shortcut here is, when you find the derivative of this function, dou by dou x of h, when you find the derivative of this, do you know how this changes? It becomes like this. It becomes like this. Hmm. Okay, this is how it would appear. So what happens is, you keep on increasing, increasing, increasing. After some stage, the rate of change will become stable, and then it will start reaching the peak. So it will it will reach here bottom. And then what happens is, because rate of change will become constant here, it won't change. Then what's happening? You are decreasing, decreasing in that way. And then after a certain point, the decreasing will become stable. And then at this portion, it will become stable. And then you start approaching this portion. So that's how the derivative would be. So what people do is, derivative of a Gaussian function, first order derivative of a Gaussian function, will always be like this. So why don't you directly take this and convolve on your image? And if you directly take that and convolve on your image, you get this. Why do you need this additional step of first taking Gaussian and convolving on your image and then taking a derivative, when you can actually have this derivative in place and then just convolve on the image? So find the derivative of the Gaussian, keep it handy. The moment you have an image, apply this onto that image. That's it, you'll get the result. Okay, so you can also find the second derivative. And when you find the second derivative, you'll get another filter, which is called as Laplacian filter. Okay, you can either have Laplacian filter with diagonals or without diagonals. Without diagonal means it will not be able to find your diagonal edges. But when you have those diagonals also, then what happens is whenever you have such a representation where you have those diagonal shapes which have to be detected, it will very easily detect those diagonal shapes. Not just that, the beauty of this Laplacian is something else, which is here. So what you do is, you first find the Gaussian, then find the derivative of this, which would appear like this. Then take this and again find the derivative of that, which will be like this. So you have a Gaussian, find the derivative of that, and then find the derivative of that once again, which will lead to Laplacian of Gaussian. This is called as second derivative. So the first derivative will give you a Gaussian like this. Second derivative will give you Laplacian of Gaussian. This is second derivative. When you have a second derivative, and when you observe this from the top, this is like your black color, this is like your white color, okay? 255 to 0. Okay, and when you observe this from the top, it will appear as if there is a round shape. Okay, and as and how you peep into that, it will look black. So this round shape, imagine that as a cone that you have. And when you have such a Laplacian of Gaussian, what kind of features can you extract is a question. So let me write it down. What features can you extract? Okay, if we have Laplacian of Gaussian filter. Okay, please think and ponder on this thought while we take a break and come back. So it is 11:30 now. We are going to connect back exactly at 11:40. Okay, it's 11:30. Let us take 10 minutes break and then let us connect back at 11:40. All right. Take a quick break and come back, friends. Come back afresh. We will take this further and we will also do practically these things on our system using OpenCV. Yep, so let's continue. So Laplacian of Gaussian, when you look at it, Laplacian filter versus Laplacian of Gaussian, there is a slight difference. So anyways, when you have Laplacian of Gaussian, since you're going to have a circle on the top, or it appears like this, right? Laplacian of Gaussian filter, you can identify blob. Blob is some kind of a circular shape, and it can be used in various scenarios such as diabetic retinopathy. Diabetic retinopathy. What happens in diabetic retinopathy is that retina of an eye, okay, is of a circular shape. And people say that if you're impacted by diabetes, it will first impact your eye. So if you're going to have some kind of sight issues, you're not able to see something properly or something of that kind, that means diabetes symptoms have creeped into you. So people just scan this, take the retinopathy, retina images, and then they determine whether you have diabetes or not. That's one thing. Second thing is when you have, say, sunflower field, there'll be a lot of sunflowers. People have built a lot of applications wherein when you have sunflowers like that, you can just take a photo of this sunflower field and then determine what is the yield. It will automatically count how many sunflowers you have. Simple. You can in fact take a video, split the video into multiple frames of images, and job done. Okay, this is something which people do. And you apply these kind of filters which will automatically determine how many sunflowers are there because it's in this shape, circular shape. Anything, any image which has these circular shapes, etc., you can identify, kind of, yeah. Now, let us understand on how do we deal with noisy images. One way to remove noise is by taking a Gaussian. This is something that we have discussed, right? If I have noise in the image, then you take a Gaussian filter and apply that. Okay, that's wonderful. So if I have noise in the image in this way, for example, this is, say, your original image, then you have salt and pepper noise. Salt and pepper noise means you'll have white spots like salt and pepper black. So you'll have white and black spots. That's salt and pepper noise. Then you can also have impulse noise. Impulse noise means just having those white dots is impulse noise. Then Gaussian noise. Gaussian noise means 0 means black and 255 means white, right? So anywhere in between you take the values, and then if say 240 or 50 or whatever be the values, if you have those kind of spots, it's called as Gaussian noise. Okay, now if you apply a 3 by 3 Gaussian filter on the image, salt and pepper noise image, this is how it appears. If you increase the filter size from 3 by 3 to 5 by 5, 5 by 5, then the amount of blur increases. It will smoothen it even more. And if you use a 7 by 7 filter, it will further smoothen. But the disadvantage here is that, okay, a clear disadvantage here is that your image is becoming blur. Okay, your image is becoming very blur. Since your image is becoming so very blur, you'll have to take an action. What action do you take? You cannot apply this a Gaussian filter when you have noisy images. It's not, it's just a basic way of dealing with the noisy images. So people proceed further with non-linear filters such as median filter. So what happens? Let us understand. When you have noisy images, say you have an image like this, and here there is no noise in this patch. If you're, this is an input image. On that input image, if you take a 3 by 3 filter and apply this 3 by 3 filter on this patch, it doesn't make any difference even if it's median, because there are no outliers per se. You take all these values 10, 11, 10, 9, 10, 11, then 10, 9, 10. Take all those values. Now, even before you calculate median, you need to first sort the data in ascending order or descending order, and then take the middle value, and that would be here. Yeah, the same number is coming up. That's fine. Then move your patch, 3 by 3 patch or filter, one stride. One stride means one pixel. When you move it one stride in this way, you take all those numbers, and here you have outliers 0, 0, 1 are clearly outliers in comparison to the other numbers. You sequence them, and once you sequence them, you take the middlemost value, which is 10. So you replace this with 10. Here also there is no big difference. However, now you will have a difference. So you have been moving your, say you have been moving your filter across your image, and you reach the final patch here. When you take all those numbers here, very clearly it is an outlier, 99. So when you take all these values, when you sort them in a sequence, and when you take the middle value, it becomes 10. So 99 has changed to 10. So this 99 could be a, an outlier. It could be a patch which appears, or a dot which appears on the image. That can easily be gotten rid of. And if I apply such a filter, look at the difference. If you apply Gaussian, the noise is not going away completely, and also the images are becoming a lot blur. But when you look at the median filter here, and when you apply on the images, the these dots are gone, and then it appears a lot more smoother. Okay, and similar to that, there is something called as alpha trimmed mean. So if you take alpha as 5%, just as an example, so what it does is, say you're applying your filter on this patch, you take all these values, sort them in a sequence, you'll have all those values, say you have 9 or whatever be it. Then you remove the bottom 5% and the top 5% after sorting them in a sequence. So you sort them, and the assumption is that the bottom 5% and the top 5% values would be like zeros and 255s, will be extremely large. So you kind of get rid of those values. Okay, this is what we do, what people do. Okay, so this is also another thing. And we also have bilateral filtering. Bilateral filtering, what it does is, it takes your image and creates an animated version of your image. Okay, it takes your image and just comes up with this animated version of your image. This is called as bilateral filtering. This is called as non-linear filter. It will smoothen your image by preserving your edges. Wherever your edges, it will not get rid of those edges. This is bilateral filtering. Okay. Another very good edge detector technique that exists is called as Canny edge detector. So just to do a quick recap before you forget about what all we discussed, let me show you this. So these are the filters that we have discussed. Okay, we have discussed about edge detectors, wherein we have Sobel, Prevet, Roberts, Canny. All of these are the various edge detector techniques. Now we are discussing about Canny edge detector, and we have also discussed about Laplacian filter. We also have a blob detection algorithm or a filter which is called as Laplacian of Gaussian. Any circular shapes it can identify. And then you also have nonlinear filter wherein you have bilateral filter. Of course, all these things we will practically do it. Okay, do not assume that this is only theory. No, we will practically implement each of these using OpenCV. Okay. There are three important features which should exist in a good detector. First, any good detection technique should respond to edges and not noise. Sometimes you'll have noise in your data, and you don't want your algorithm obviously to respond to uh, noise. You want your filter to respond only to edges. Wherever there is an edge, you want your filter to detect that. Okay, and then there is some good localization. That means your filter should help you detect an edge with good localization. That means detect the edge near the true edge. Wherever there is an edge, you need to detect that. Wherever there's a non-edge by mistake, you should not detect that. Okay. And then it should have a single response. One per edge. Single response. It should not be like this. If I draw like this and if I say, okay, this is the edge, then you should, I mean, that's not right. There should be a single edge, not bunch of edges. Okay. Now let us take this input image and let us solve this. You take an input image and then you apply a Sobel along x-axis. Then you apply a Sobel along y-axis. We already discussed about Sobel edge detector, right? If I move along the x-axis, what kind of edge will your model detect? Let me ask this as a poll question. If I move along the x, or if I apply Sobel along x-axis, what edge will it detect? Let me see. So a new poll question. If we apply Sobel filter along x-axis, then what edge will the filter detect? Okay, would it be vertical or will it be horizontal? Please, can you answer this? Wonderful. 90%. Oh, the count is dropping to 80%. But then again, I think a few of the people are trying to push it hard towards the higher percentage. Yep, you guys are right in saying that. I would say 85, right? I think that, yeah, touch 85, please. 84. 85. Good. I'll quickly escape from there before the count drops. Yep, you're right. If you're moving along the x-axis, you're moving in this way. When you're moving in this way, you clearly see that there is an edge over there. Okay, there is an edge here. And that's the edge that you're seeing here. Okay, that's the edge that you're seeing there. Okay, so that's how it is basically. So when you move along this, when you move along the y-axis in this way, then this edge is not visible because when you move in this direction, there is no change along this. So there is no edge here. It doesn't appear. So if you want to find all the relevant edges, then you have to actually apply both Sobel along x and Sobel along y-axis. But then, can I at one go identify the edges both along x and y direction? Yes, that is called as Canny edge detector. But then all it does is, it is going to apply individually Sobel along x and Sobel along y direction, and then it is going to combine these two. This is the symbol for gradient, rate of change. So how do you combine in this way? You're finding the magnitude of rate of change, and you're combining the rate of change along x and also along y direction, and then you square it and take the square root of that, right? When you square it and take a square root of that, then this is how it appears. And when you find this gradient, take that gradient and say if that gradient is greater than or equal to threshold, then what happens? Okay, if that gradient is greater than or equal to threshold, you're getting a value which is, this threshold is empirical. Okay, let me write it down. Meaning there is no defined rule on what should this threshold value be. It keeps changing. Okay, the threshold value keeps changing. It won't be the same. Okay. If this threshold value is, say, 25, what do you mean by that? If the rate of change here, only if it is greater than or equal to 25, you'll get some number. If it is greater than 25, only consider those kind of changes. If the rate of change is very less, okay, then do not consider. For example, if the rate of change is say 20 or 18, that means the rate of change is so less. The rate of change, if you're moving along, here, if the rate of change is very less here, it shouldn't be detected. You don't want such a small change to appear. Only if the change is significant or greater than 25, you proceed further. This 25 is a number which is empirical. There is no defined thumb rule on how to choose that. You can choose. It depends on the application that you're working with. If you're working on a, say, radiology image, cancer prediction, then even a small change matters. So maybe you'll reduce the threshold to 10 or maybe to 5. Who knows? Right? But if you're working on social sciences kind of a project, like typical projects that you do, then you need not have such a low threshold. Right? That's one thing. So you first apply Sobel along X and Sobel along Y. Okay, you do that. And then you find the gradient, rate of change, by combining those two. And this is the image that you get. And here what you do is you apply a threshold saying that only if the changes are greater than something, consider that. Otherwise, do not consider. When you do that, every change which is pixel value, which is black, goes away, dead black, and then this is the kind of image that you get from that. There is again a disadvantage here. What did we talk here in this? There has to be a single response. That means you need to have a single edge. But if you look at this image, and if you look at this portion, yeah, if I were to put it here, it's appearing like this. We want a single edge. We don't want it in that way. Then how do I fix it? Then your computer vision experts sat down, thought a lot, and then they thought, okay, we can fix it. And then they came up with a concept called as non-maximum suppression. Okay, they came up with this logic called as non-max suppression. What is this non-max suppression technique? Okay, so here, this is the thick rate of change. This is a thick rate of change that you are observing here. Then what happens is, you take a value, a number here, okay, and then this you call it as x comma y, and then take one number which is ahead like this, which is x prime y prime. Then you take another number behind this, which is x double prime y double prime. And then now look at this. Look at, is the rate of change at this x comma y greater than the rate of change at this point, which is a new point? That is one thing. Second, is this rate of change at x comma y also greater than this number? So if the rate of change here is more than one which is ahead, one which is behind, then this is the winner, right? This is like winning on this, and this is also winning on this. So if this is greater than this, and if this is also greater than this, then the end result would be this. Correct. Otherwise, you say it is zero. I mean, you have to proceed further. I'll repeat. Then what happens is, you say your point is here, then you take one point here, take another point here. If the rate of change here is greater than this, and the rate of change here is greater than this, then this is the winner, the one which is in the middle. It's like first, second, third positions, right? If one is greater than this and this, only then it'll be in a first position, right? So only then you take that as the true edge. Otherwise, you say, hey, that is not the true edge, and then you move on again. Again, how do you move on? Say you were here, you took one point here and one point behind. Now what you do is, say this point is greater than this. So what do? You take another point here. Okay. And then once again do the same thing. Check whether the rate of change here is greater than this and this. If yes, this is the edge. Otherwise not. And then this, you do that throughout the image like this. Throughout the image. And then take throughout the image, and then throughout that keep doing the same task, and then keep identifying the point where you have a maximum change, and then apply that non-maximum suppression. The moment you apply, you take the image, this image is this. That means you take an image, find the Sobel along x, find the Sobel along y, it will find the edges along x, along y, combine those two, okay, and then do a non-maximum suppression. Once you do a non-maximum suppression, Look at that here. You have the thick edge, but it has become a thin edge. After that, apply the threshold. If the values are greater than 25, greater than or equal to 25, only consider those. So you'll get an image like this. But there's again a problem here. As opposed to this image, or as opposed to this image, look at here, it's not so noisy. Here also, it's not that noisy. But when you look at this, it's looking very, very noisy. These edges are all like hanging threads, right? A lot of spurious edges exist in comparison to this, right? In comparison to this has a lot of spurious edges. This will make our life very difficult in identifying the edges. Hence, against your, computer vision experts are taken aback because there is again a roadblock. Again, they sat, again they thought on how to solve, and they came up with yet another technique called as hysteresis thresholding. What did they do in hysteresis thresholding? They took all these edges, all these spurious edges, and they formed a rule saying that I'm going to come up with a lower threshold and upper threshold only if your edge, whatever are those edges, if they are crossing the high, I'm going to treat this as an edge. If something doesn't cross the high, I'm going to treat this as non-edge. The moment you treat in this way, what happens is all these hanging threads kind of things will be gone. And there's one more thing, which is if there is anything which is below low, obviously it is non-edge. But then if something falls in between high and low like this, but then if this edge connects with another edge which crosses the high, then this will also be considered as an edge. Okay, if something is like this, just falling in between high or lower high, or something which is not crossing high, but if it goes and connects with another edge which actually crosses the high, then you start treating that as an edge. Okay, so here, if the gradient at a pixel is above high, you straight away say that it is an edge. If the gradient is below low, you say that it's a non-edge pixel. If the gradient is between high and low, then declare it as an edge if and only if it is connected to another edge pixel directly or via pixels between high and low. Right? These are the three rules that people came up. And again, this is a heuristic. Right? Again, this is a heuristic or empirical values, meaning you keep changing this value and this value, keep checking your results. Wherever you get a best result, you choose that. Okay, so here I'll give you steps on what we have done exactly. So let me choose a white screen. Let me write it down. Number one, take an image and apply Sobel along x-axis and apply Sobel edge detector along y-axis. Then combine these two. Combine the change along x and change along y. How do you combine it? You just say magnitude of change is equal to change along x plus change along y. Of course, you square, so you also take a square root of that. Then, since there might be thick edges, To get rid of that, you apply non-maximum suppression. Something, if some change is not maximum, then suppress it. Suppress changes which are not maximum. That's called as norm. This will give you a thin edge. From thick edge, you get a thin edge. Then once you get this, what do? You are now going to get another problem, which is spurious edges like hanging threads. How do you get rid of that? By applying hysteresis thresholding. Here you need to provide a value high and low. This is empirically chosen. And finally, after all these things, you put a threshold greater than or equal to some number, for example, 25. And then finally, you get an image with edges. And this image with edges is taken for further processing. Okay, perform further processing. Whatever you want. Maybe you want to use this image for prediction purpose. Do it. It'll be faster, easier. It will take less memory. All these other advantages that exist. The next thing that we have is okay, sorry about that. So the next thing that we have is this image sampling and interpolation technique. So image sampling and interpolation technique is very, very important in terms of reducing the size of the image or in terms of increasing the size of the image. Usually image sampling is is related with subsampling. This is correlated with subsampling or reducing the size. Interpolation is usually correlated with making your image bigger from the given size. So question to you all is, if this image is very big, how do I reduce the size of the image to half? How can I generate an image which has half the size of this original image? Can someone answer this? Can anyone answer? I give you an image, and if I say that make the image half the size, how would you do that? Quickly. I request everyone, just think out aloud, give some exercise to your brain, and can you do this? Let's see how many of y'all will get it right. Okay. Simple, friends. You remove every alternate row and column. So if you have this image which is of size say 28 by 28 or maybe 28 by 38, something on these lines, what you do is you remove every alternate row and every alternate column. So this will become 19 by 14. It will become 19 by 14 basically, right? And then if you have an output image which you get here, if you are going to reduce this even further, and if you remove every alternate row and column again, this image becomes 1 by 4th. And on this image, if you once again remove every alternate row and column, it will become 1 by 8 the size. And now, if I keep reducing the image in that way, and all these reduced sizes, if I zoom to map this, so now if I just maximize this in this way, okay, and if I make this image also as bigger as this image, then let's see how it appears. Look at that. There's a lot of cruftiness, meaning it's all a lot blur. Okay, you're reducing it to half, then you're reducing it to 1 by 4th, and you're reducing it to 1 by 8th. But then when you zoom it back to this size, look at that, a lot of meaningful information is gone, lost from your image. Since a lot of meaningful information is lost from your image, this is not the right way to reduce the size of the image. Okay, so we have to look at something called as image subsampling. Very, very important. If you do not sample the image properly, you'll get these kind of things, which is called as aliasing effect. Aliasing effect means when you have an image, but you're reducing the size of image, but you're not maintaining the subsampling logic. Okay, so look at this portion, the upper portion of this. It all becomes okay a lot more. This portion, if you observe, it's becoming a lot, you know, it's losing the shape basically. This is called as aliasing effect. Here also you have that aliasing effect. It's like that. The image is not proper. Here also the image is not proper. You're getting a different shape altogether. So to counter that, people have come up with a concept called as Nyquist rate. Okay, Nyquist rate or Shannon's sampling theorem. Nyquist rate or Shannon sampling theorem says that whenever you take a sample or whenever you reduce the size of the image, ensure that the reduced size is greater than or equal to 2 times of maximum frequency change. Hey, what does that mean? I'm lost. Don't worry. I'm here to walk you guys through. Do not worry. Let's understand. Say you have an image like this. Okay. What does Nyquist rate say? The minimum sampling frequency that you choose should be greater than or equal to 2 times of maximum frequency change. If you take this portion of the image, if you take this portion of an image, you have one maximum change from black to white. Here is where you find that change from black to white. So maximum change is 1. So sampling frequency should be greater than or equal to 2. 2 times of 1 is 2. And here what you're doing is you're choosing 4, in total 8, right? You're choosing 4 points here and you're choosing 4 points here. 4 plus 4 is 8. This 8 is obviously greater than or equal to 2. So this is a good sampling strategy. Let us look at this image. Here also you have this change. You have one change, which is maximum change from black to white. There's one maximum change. So sampling frequency should be greater than or equal to 2 times of maximum frequency change. So it should be greater than or equal to 2. Since it is greater than or equal to 2, and here you should have minimum 2. Here you have 1, here you have another. Okay. So here you have 1 and here you have 1. So you have 2. This 2 is greater than or equal to 2. Since it's equal to 2, you choose that. Okay. Then you have another value here. Here there is a rate of change from white to black. Okay. And here you have one value and here also you have another value. So you're choosing 2, at least 2. Should be greater than or equal to 2 times of maximum frequency change is only 1. Right. So this is also a good sampling strategy. How about these two? Let's see. So if you observe this, there is one change from black to white. So the maximum change is 1. 2 into 1 is 2. So minimum frequency, sampling frequency that you're going to choose should be at least 2. But here you're choosing only 1 in this. So it's a bad sampling strategy. Same is the case with this also. Here it is fine, but here it's not fine. And here it is not fine. So because here you're choosing 2, that's fine. But then when you look at this patch, you're choosing only 1. It should be minimum 2 because the maximum frequency change from white to black is 1. Okay. This is called as Shannon's sampling theorem or Nyquist rate, and we have to fix to that. Another thing is called as wagon wheel effect. So let me show you a video. Let me play a video so that it starts making sense. There is this falling helicopter. Illusion. Or yeah, this one. Okay, if you look at this, or maybe this one. You look at that, and it is giving you an illusion as if this helicopter is just flying like that. Okay, without the wings rotating, right? You're getting that illusion basically. Even when you look at your fan, ceiling fan, sometimes you get that kind of an illusion. Right? Why is a question. Because of something called as wagon wheel effect. What happens in wagon wheel effect is that, you know, at the blink of an eye, if this is your wheel, okay, I can also show you that, you'll get an illusion as if your wheel is rotating in the reverse direction, right? Let me show you that. Okay, let me go here again. Our wheel reverse illusion. You might get a sense that the wheels appear as if they are rotating in a reverse direction. Which one should I play is what I'm thinking. Yeah, let's see this one. Yeah, look at this wheel here. The feeling as if it's not rotating, or sometimes you might get an illusion that it's rotating in the reverse direction. Reverse. So that's fine. So why do you get such an illusion? Is a question. Because of something called as wagon wheel effect. Your eye, human eye, will blink sometimes, right? And we blink at a certain speed. And when you're traveling at a rapid pace, what happens is When you close your eye, your wheel would have moved here, then moved here, and then maybe it is here. Within one blink of an eye. So you are watching this. The moment you blink, okay, the moment you blink your eye, that means you open and close your eye, you'll find as if your wheel point is here. Okay, and a blink of an eye, you'll feel as if you're here. So what illusion you'll get? First you're seeing this, next you're seeing this. You missed out this, this, and this. This moment you missed out, and you're seeing this. So you'll feel as if after this you're getting here. So you'll feel as if the wheel is rotating backwards, counterclockwise. Okay, this is the kind of illusion that you get. Okay, so these are two things that you need to remember: Nyquist sampling rate, and also this wagon wheel effect. Now let's take this image. We discussed that when you subsample, meaning when you reduce the size, or when you downsample, all mean the same. Downsampling, subsampling mean the same. When you do that, you first need to apply your Gaussian filter. Means what? You take your image. See that somewhere here? Yeah. First, I'll explain this and come back. You take your image. Okay. You first apply a Gaussian filter on the image. Then subsample. Then again apply a Gaussian filter. If you want to again subsample. Again subsample. Again take your image. You apply a Gaussian. And again you subsample. Keep doing it. When you keep doing it, the beauty is that you'll have something called as Gaussian pyramid. I'll give you a practical application here. Say you're using Facebook. On Facebook, say you uploaded your photo, uploaded your team outing photo. And your Facebook gives you an option to automatically tag your friends. Tag your friends. Meaning, say you're uploading a photo, group photo, wherein you also have my image. So here you are there, here I am there, and all that. So what Facebook does is, Facebook is going to look at, if this is you, it's going to look at all of your friends. It will quickly look at what kind of profile pictures your friends have. Okay, and say you have a close-up image. This is me, you and me. This me is my face, which is a close-up image. So this will have a bigger size as opposed to this. This will be very small. If you want to just crop the face, this is very big. Then how do I do a mapping? When I take this and try to apply here, this will be a big patch, big patch. But then this image is having a small patch. So how do I map it? We can map it if you have Gaussian pyramid, wherein I have image. This is my image. I'll subsample, 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 so on and so forth, until it becomes small. And this, when I apply here, there can be a match. If I apply big images here, I cannot find out. But if I can apply, say, this patch, maybe it will identify the image. In these kind of scenarios, you need Gaussian pre-filtering. So you apply Gaussian, subsample, apply Gaussian, subsample, apply Gaussian, subsample. In this way, don't directly do it. Don't directly do it. Apply Gaussian, subsample, apply Gaussian, subsample. Okay. Now when you subsample in that way, and when you zoom your image, this is how it's going to appear. But when you do not do that, it will look like this, very, very crafty. Take this simple example of a text. Say you're scanning the text and then you want to automatically enter that into your database. You don't have time and energy to type it. Okay, and we have done a project for State Bank of India wherein you have your loan application, right? When you fill your loan application, you enter the details such as name, address, gender, phone number, email ID, all that. Now, what usually happens is the people who collect the application form from you, they will come back and enter all these details in a database. Okay, they enter all these details in a database. Manually, they do it. This is called as brain drain, underutilization of human potential. Why do you do this when you can automate this? So what people usually do is they scan this, they apply these kind of algorithms, and automatically they put that in the database. They automate these tasks. That is exactly what we have done. Of course, we have used something called as horizontal projections and vertical projections, but then this is how exactly they do. At that point of time, you should actually, if you directly do a subsampling, this is how it would appear. I mean, there is nothing which is visible. But then if you apply Gaussian, okay, if you apply a Gaussian filter, this is how it will be. And on that, you do a subsampling. And then you get this. Okay, that's how it will be. This is an anti-aliasing effect. Look at this and look at this. You're having all those patches, yeah? Okay, so that's how you build a pyramid of images, and you can use it for satellite imagery that you get. Just that you keep reducing the size of the image. Apply Gaussian, subsample, apply Gaussian, subsample, apply Gaussian, subsample. Keep doing that. And it's easier for image recognition. So one more quick thing that we will discuss before we before we take a break, because after the break I want to get started with hands-on. Okay, hands-on exercise. So please pay attention here. If you are given a big image, how do you downsample it? We have looked at it. Apply Gaussian, subsample, apply Gaussian, subsample. Keep doing that. But then if you have a smaller image and if you want to make it 10 times bigger, what would you do? One simplest way is, if you have say 5 by 5, then repeat each row and column say 10 times. Take each row, repeat it 10 times. Take each column, repeat it 10 times. That would make your image 10 times bigger. Okay, but that's not the best way out. So we have a few image interpolation techniques such as nearest neighbor interpolation. So let me explain that using this. Nearest neighbor, linear interpolation, you have bilinear interpolation and bicubic interpolation, etc. With that we'll end, but then let's understand this. So here, linear interpolation means, say you have an image like this. So it's a 2 by 2 image, okay. You want to make it, you want to enlarge it. So that means you want to add an additional row and an additional column. In that case, what do? You need to add, say here, one value. Okay, so what you do is you take this and this. You take one value here, which is this one, and you take one value towards the right, which is this one, this part, and then find out how far away is this pixel from this and how far away is this pixel from this center pixel, and then simply multiply. That's it. So if you want this pixel value, if you want this pixel value here, all you're doing is you're saying 1 minus a into the pixel which is towards the left, this one, plus a into the pixel value which is towards the right. That's it. The moment you could do it, issue is solved. And if a equal to 0.5, meaning you'll have this equidistant. So 0.5 into this plus 1 minus 0.5 into this. So that means you're giving equal weightage to the pixel which is on the left side and the pixel which is on the right side. And whatever value you get, that will be this new pixel. Same is the case with this also. If you want to fill something here, you take one pixel towards the left, take one pixel towards the right, and then solve it. If you say a equal to 0.5, you're giving equal weightage to the pixel on the left, equal weightage to the pixel on the right. That's it. You apply it and you get the central pixel value. If this pixel value is 10, if this pixel value is 20, so 0.5 into 10 plus 0.5 into 20, which will be 15, you replace that with this. That's it. Simple. For this also do the same thing. If you want the pixel value here, then first do it in this way, right? So what do you do? First, you need to find this pixel. Let me put that in pink color. First, you need this pixel value, this pink color box. Okay, to get that, what do? You take one pixel towards the left, one pixel towards the right in this direction. So that is this and this value. So do 0.5 into this plus 0.5 into this, 0.5 into this plus 0.5 into this. Whatever you get, you'll get here. Then you have to find this pink pixel value. Once again, do the same thing, wherein you do 0.5 into this plus 0.5 into that, you get the central pixel. Once you get these two, finally you once again apply in order to get this central pixel. 0.5 into this plus 0.5 into this will give you the central pixel. This is called as linear interpolation. Then you also have bilinear interpolation. Bilinear interpolation means if you want to find a pixel value here, you take all the four bordering values. In linear, what did we do? If you want a pixel, take one pixel towards the left, one pixel towards the right. 0.5 into this plus 0.5 into that will be the central pixel. But in bilinear, you consider all the bordering pixels. So if you want this pixel, look at this pixel, this, and this. And you solve it. If this is I comma j, then it's you write it in this way: 1 minus a into 1 minus b into this, plus if you want this, it will be a into 1 minus b into this function of this, plus if you want this, this is like a comma b, a into b into this, and if you want this part, it'll be 1 minus a b into this. I mean, this math is very trivial, okay? And then you also have bicubic interpolation. Okay, just to do a quick recap, or we will take a break and then I'll do a recap and then we'll proceed further because it's 12:40. I think it makes sense for us to take a quick 10 minutes break and let's come back. I will do a recap and then we will do uh, all these things that we have discussed using OpenCV. Okay, let's take a quick break and come back. All right, so let us proceed further and take this discussion further. So we need to first discuss about, or let us do a quick recap. First, we discussed about edge detection filters. As part of edge detection filters, okay, we discussed about a lot of filters, but then Canny edge detector is one amazing edge detection filter. Okay. Apart from that, you also have Sobel, we have Privet, and we have Roberts. Okay, and then we discussed about Canny edge detector. Next, we switched gears to image subsampling or downsampling. And we have also looked at upsampling. In upsampling, it is called as interpolation. In interpolation, we have linear interpolation, bilinear interpolation, and we have bicubic or cubic interpolation. Okay, and now what we shall do is I'm going to resort to Python, and we are going to solve, or we are going to do this OpenCV stuff. For this, I need to get the OpenCV program code, and we are going to use this. So here we have the data. Okay, and we have covered until here wherein we split the data. Okay, now we will do a lot of transformations on the images. Okay, a few of them will be a lot of fun. A few of them will be extremely important for us to proceed further. Okay, and then we will discuss about various things. Today, I think I need to also enable the webcam. And then I need to show you something very, very interesting. So we'll look at image translation, and that's the first thing that we're going to look at. In this image translation, what we are going to do is we will again same thing, we will import. I'll first let me remove everything so that I free up the memory. I'm importing CV2 and I'm importing numpy as np. Then you have cv2.imageRead. Okay, so we want to read the image. Let me read that image if this exists. Wonderful. So the image is of 256 by 256 by 3. 3 means it has 3 channels, 3 color channels. 256 rows, 256 columns, and 3 color channels. Okay, and then if you do this, wherein say image.shape colon 2. Okay, colon 2 means 0, 1, and 2. You're taking 0, which is 256. Here again you have 1, which is 256, and 2 here is 3 channels. Okay, you have number of rows and number of columns. I'll run it. So you have number of rows, which is 256, and number of columns, which is 256. And then you're doing some translation. This translation matrix or transformation matrix is as follows. you have 1001, and 1001 is called as identity matrix. You see 1001, it's called as identity matrix. This component means take the image as is, identity matrix, and then you have a translation along x and translation along y direction. Okay, translation along x is 70 and translation along y is 110, 110. So we have translation along x. You are moving along x, that is, you are moving along x in this direction, right direction. When you say translation along y, you'll be moving along the downward direction. Once we create a matrix like this, okay, you put that into something called as translation matrix here, and then you do cv2 dot warp affine. So once we create a matrix, we use the function warp affine to apply it on the image. So you have an image and you apply a translation matrix on it. And when you apply a translation matrix, there is also another argument, or these are called as flags, FLAG. Okay, in this third flag, basically, or here, what you're giving is, sorry, this is not a flag, this is an argument, my bad. Okay, this is an argument that you have. So you're saying I want number of rows and columns as that of the original image, and then cv2 dot interlinear. This is interpolation flag. Interpolation flag. And you're doing an interpolation here. Okay. So what would happen? Let us see. So you're taking an image, applying a translation matrix, and you're saying, I want the window size to be similar to the original image. If the original image is like this, you want the window size of the output image also to be the same, and you want to do linear interpolation. And then you say cv2.image show. In that you want translation. Okay, the window name should be translation, and within that you want this translated image. Let me run it. There we go. So you knew on how our original image was, right? So you're ensuring that whatever size you have, this is also of the same size, but then you're trying to move it 70 pixels towards the right and 110 pixels towards the bottom down, and then you have your image. Now there is yet another translation. What are we doing here? I'm saying that, okay, since this image is getting just cut there, it's getting disconnected there, kind of, you're not able to see the complete thing. So if I were to see the complete image, what I will do is I'm going to extend this. In the output that you're seeing, I want to extend the number of columns by 70, because you have 70, I want to extend it by 70 here. And here you have 110, so I want to extend it by 110. Okay, the same thing again. I'm importing CV2 and NumPy. I'm reading the image using cv2.imageRead. Then I'm saying number of rows and number of columns is equal to image.shape of 2. Means what are you doing? Image has a shape. Image has a shape of 256 by 256 by 3. This 256 has index number 0, this has index number 1, and this has index number 2. If you say colon 2, all you're saying is you want 0 and 1. Whatever comes here, that is ignored. Okay. 0 means 256, 1 means 256. Okay. Take those many rows and those many columns here. And you load it. So CV2, NumPy, this, and this. Then what we are saying, NumPy dot float. You are now creating a translation matrix. And as we have already seen, translation matrix will have 1, 0, 0, 1, and 70 and 110. So it's 1, 0, 0, 1, translation along X and translation along Y. Translation along X is 70, translation along Y is 110. You have it. You run it. And then you say cv2 dot warp affine, take the image, the size of the window of the output that you see is this size, then number of columns plus 10 and number of columns plus 110. Run it. And then you see the image. Okay, so you have the image here. So it came, right? Your box size ideally would have been like this. But what you're doing is you extend it by 70 pixels here. You extend it by 110 pixels here. And this is how you get. Now you can even further extend the image, the window size. You can say, okay, this time let me do one thing. The number of pixels along the columns, I want to extend it by, if your original size of the image is so much. When you displayed the image, it was appearing like this, only in this portion. So you increase by 70 and 110 so that the entire image was visible in the window. This was the window size. Now you are again extending this by 30 and 50 so that the window size in which you see the image further extends. cv2.warp-affine. Warp-affine is a function that you use whenever you want to apply any kind of transformations, like the translation that we are using. Any kind of other transformations can be applied. For that, you have to use cv2.warp-affine. When you run it, why is it going in this way? This is not the right thing. Okay, now I get it. So why that problem is arising is because I should have run this code also. Okay, we need to import the new image. Otherwise, it will take only that old image and do it. Why? Okay. Sorry, let me restart this. Okay, now let me run this once again. Mhm. One second, let me run it. CV2, NumPy, read the image. Okay, number of rows, columns. You have a translation matrix. You're applying it, and then you want to view this image translation of translation. Yep. Yeah, here we go. Right. This is the kind of I don't know. Okay, sorry, my bad. Again, I've run this border pixel wrap. What's going wrong with me? Okay, so sorry. Let me run these once again. Importing the files, loading the image, number of rows and number of pixels have been taken. And it's 256 and 256. Here we have the translation matrix. And I'm applying a warp affine. This, I'm taking the input image. And then we are applying the translation matrix. Let me store it here so that I do not get confused. All right. So we're saying image translation matrix, and we are just extending the window size further, and then you can view the image. Now I think things should be fine. Yeah. Ideally, this is not the image that you should see. Sometimes your system is pretty tricky. That it happens, most of the times. Let me restart the kernel. The window is gone. It happens most of the times because it saves the previous images in memory. The moment it saves the previous images in memory, it throws these kind of issues at you. That's fine. It's part and parcel of the programming. You will have to any which ways live with it. Now, there we go. This is the right one which we wanted to see. So what we have applied is we translated the image 70 pixels towards the right and 110 pixels towards the in the downward direction. But then what you're doing is here you're saying number of columns. If I keep it as is as the original stuff, it would get cut and you'll be able to see only this portion. So what we have done is we have added 70 pixels. So whatever you're moving by 70 pixels, you're adding those many pixels on this side. So the entire image would be visible on this side. Since you're taking it down by 110, you also want to add 110 rows here. Okay. And then you're adding another 30 here. And you're adding another 50 here. So this becomes big. Right? This is what we have done. And one more thing is, when you have those border pixels, what do you do with that? Say I'm translating the image by 70 and 110. Okay. If you just do a translation, what would happen is you will be moving your image 10 pixels or 70 pixels towards the right and 110 pixels downwards. And you're saying now that I want to apply this translation, whatever is being applied on the image. And then I want to take this image and then apply this translation matrix on that image and the resultant. So this is your input image that you have taken. You're applying this operation and then you have an output image. This output image, you want to display it in a window size, which is similar to your original image. Your original image, if it is 256 by 256, you want to use the same window size to display your image. And here you're applying linear interpolation for the missing pixels. Okay, and you want to do a border. You want to do a warp affine. Okay, so you're doing a border wrapping. Sorry, not warp affine. You're doing a border wrapping. We discussed about the border pixels issue, right? Bordering effects. How do you handle this bordering effect? You do clamping, you do wrapping, all that. So we are trying to do this wrapping. And one means you want to take one pixel and move it throughout. So let me run it and then explain it once again. Yep. So what is happening here is the window size will be the same. You're moving your image by 70 towards the right and 110 downwards. Okay, and then what's happening? You're doing an interpolation and you're having a border wrapping. So you take the last pixel, you move it throughout. You take the last pixel, you move it throughout. You take the last pixel and move it throughout. Okay, and then here. We can also rotate the image. There is also something called as image rotation. How does this work out? Okay, image rotation means you want to take what you're doing is you're importing the required libraries and you're loading the image using cv2.image read and you're giving the complete path of the image and you're loading that. So let me run the first three lines. Then you're going to your image dot shape, which will give you 256 by 256 by 3. You're just taking 256 and 256. Index number 0 and index number 1, and you're storing it in number of rows and number of columns. Then you're applying this function called as get rotation matrix of 2D. You're saying get rotation matrix 2D, wherein you're saying take the number of columns by 2 and number of rows by 2. So if your image is this, if you say number of columns by 2, you count all the number of columns, and if you divide it by 2, you'll get at the center. If you say number of rows by 2, you take all the rows and divide it by 2, so you get to the center. So you'll get to this middle point, okay, because you're taking number of rows by 2 and number of columns by 2. And then you're using 30. This 30 means shrink the image by 30%. Shrink the image by 30%. Make it small by 30% from all angles. If this is your image, reduce from all the angles and then make it shrink by 30%. Okay. So by 10%, 20%, 30%, shrink it. And then what you do is, sorry, my bad. Okay. This 0.7 means that you want to shrink it by 30%. Okay. That means you want only 70% of your image. Okay. You want only 70% of your image. Okay, that is the meaning of this shrinkage. Sorry, this 30 here that you're seeing is a rotation. By what angle do you want to rotate? And here you're saying that you want to rotate this by 30%. So you have this rotation matrix, cos theta minus sine theta and cos theta. Okay, you'll have the rotation in that way, and you're saying you want to rotate the image by 30 degrees, and it will rotate the image counterclockwise. Counterclock, not clockwise, not in, if your image is like this, you want to rotate by 30 degrees, not like this, but you want to rotate it like this, counterclockwise. So if I were to run this, let's see what happens. So you're getting that rotation matrix in place, and then you're saying cv2.warp affine. You take the image, apply the rotation matrix, and ensure that the output image has the same number of columns and rows. There we go. Run it here. Yeah, this is how it's going to be. So you take the center and then you rotate it counterclockwise, anti-clockwise by 30 degrees and shrink, make your image smaller by 30%. So only you have 70% or 0.7 of the image. This is another thing. Then there are multiple ways of rotating your image. Okay, all these are those different ways of rotating your image basically. You can do the translation and rotation at the same time. So what you're doing here is you're taking translation matrix, you're doing the rotation of that, and then first you're applying the translation matrix, and then you're applying the rotation matrix, and then you're taking this translated image and then applying the rotation on that. So you do the translation matrix, rotation. You first apply translation and you get the output. Take this translated image and then apply the rotation on top of that. Then you have the rotated image. There we go. Translated and rotated. And you're not shrinking the image. You're taking the same size image. You're rotating it by 30 degrees counterclockwise, and then you're using it further. Okay. And this part, if you're a little confused on this part, it's very, very easy. Translation matrix. Again, it's 1001 and translation along X and translation along Y direction. So translation along X, all you're saying is take 50% of number of columns. In your original image, number of columns is 256. 50% of that, 0.5 into that would be 128. All you're saying is, let me take 1001 and 128 here. That means move your image 128 pixels on the right side, and here also you're doing the same. You're saying 0.5 into number of rows. This is rows comma columns, right? Rows, columns, both are the same, so that's fine. So you take number of rows, multiply it with 0.5, so you get 128. So move it downward by 128 pixels. So you're just moving it down in that way. Okay, that's the meaning of translation. And since you're moving it down by in this way, how it would appear your image, if your original image was like this, then it will move in this way. Hence you're saying your output image, when you do this, your output image should be twice as large as this. So what would happen then? You'll add, you're moving it 128 towards the right, so you're adding 256 here. You're moving 128 here, and then you're adding 256 here. 128, 128, 128, 128 in that way. Okay, and then final thing, we can actually resize the image, and when you resize the image, what we are trying to do here is we are using a factor. So I'm importing CV2, we are loading the image, and when you say cv2.image show, it will show you the image, and then you have a scaled image. What you're doing is you're telling cv2.resize the image. Okay, and how do you want to resize it? When I say none, the output image, none means it should be the size of the same input image, the window size. I'll show you that. And here you're increasing it by a factor of 1.2 along X and 1.2 along Y, and then you're doing interpolation, which is cv2.interpol. So you're enlarging the image by 20% on X and Y direction. Then you're doing a linear interpolation. That's a linear interpolation image that you want to see. cv2.image show means you want to see this scaled image and you want to give the name of that window in which you have the image as scaling hyphen linear interpolation. Then you want to do cubic interpolation. Then you want to do area interpolation. Same thing. Let me run this. And you'll have all these images. So you have this image. Where are the other images? Let me do this. This is the original image. Then you have the scaled image. Then you have this image. Finally, you have the skewed image. Okay. So this is how the images will look like. So you have your original image and okay. So you're taking your original image, you're increasing it by 1.2 or 20%. When you increase it by 20%, what are you doing? You're increasing the size of the image. So if I were to go back to this, what did we do here? We were discussing about this, that if you have an image and if you want to make it bigger, that's called as upsampling or interpolation. Okay, and we discussed about the various interpolation techniques. And when we do that, and when we expand this, you have to fill the additional pixels. So you're just using a linear interpolation first. Then you're also trying out something called as cubic interpolation. And if you want to make your image look very big, right, you can do this skewed size. You're just increasing the window size like this. So in this way, you can play around with your images, right? You can reduce the size or you can increase the size. Okay. All these are done using translation matrix. So I'll stop here and a quick housekeeping things. So quickly, we have the attendance form which is placed here. Okay, and please give your feedback. Yeah, Ramesh Kannan, you can do it. You can write a loop and then do it. Okay. Yeah, we will learn that. We will learn all that, Supriya. Okay, so for now, please give your attendance. Okay, and you'll get a certificate upon your attendance. It's posted here. If you want me to post that here, I'll do that. There we go. Attendance form. And here is the LinkedIn, sorry, not LinkedIn, YouTube video link. Please click on that, subscribe so that you watch the future videos. Yeah. And the quiz will be posted on our Facebook and LinkedIn. Practice it so that you will get to learn new things. All right. And a few of y'all, yeah, you need to practice, Satish. That's the only way out. You might get confused, but if you practice twice or thrice, things will fall in line because you're looking at this for the first time. That's what happens. Yeah. And then a few of y'all were asking for my profile. I'll share it with you because I don't know. A few of them were complaining that I shouldn't be sharing, but then that's okay. Few of you all are asking, so I'll put it here. I received some personal messages, so I responded to you all personally. But if you want to connect, that's the profile. Yep. All right, friends. No, it's there. We will not provide any screenshots of code in learning management system, Rajkumar. The reason being, it's already there, recorded. Right? For example, if I open this, it is already available here, entire code. Okay, you just look at this and then you can answer. You can type it on your own. Yeah, yeah, Nagraj, you'll get it. Yeah, you first complete this, Satish, and you can reach out to me. I'll have a conversation with you to understand your understanding, and then I can share more. Okay. All right, friends. Thank you so much. Attendance link is provided on the chat window. Once again, I'm posting it. Thank you all so much. No, no, it won't be. It won't be. Let me know which part is blur. I will open that in the class and then show you. Yeah. 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 Thank you so much, Shiv Prasad. It's a pleasure. Okay. Thank you all. Okay. You just double click to expand the mind map. Yeah. Thank you all. Bye.